Now, let's talk about absolute extrema. So, last time we talked about local extrema, which were the biggest points near that point. So something that looks like a little hill or a little valley in the function. Now what we're going to talk about is if you have a function defined on a set, how do you find the absolute biggest value or smallest value that it spits out? We're going to call those the absolute maximum and minimum respectively. So first of all, we have a fact, and this fact is called the EVT. And this says if f at x is continuous on a closed interval, it has an absolute maximum and minimum on that interval. This might seem obvious, but careful. We don't have to have maxima or minima existing necessarily. So an example is, okay, let's take f at x is equal to 1 over x on this open interval here. Well, what does this function look like? This is a classic example of a function that blows up near 0. The graph looks like this, and the function values get arbitrarily large as x gets arbitrarily close to 0. Yes, this is continuous on this interval, but it certainly doesn't have a maximum. So we're going to need the function to be at least an open interval isn't enough. I'm claiming here that a closed one is, but note that an open interval isn't enough. And of course, we don't have to draw a picture of this because, of course, all sorts of things can go wrong, but if your function's not continuous at all, you can't necessarily expect maxima or minima to exist. So let's do some examples of functions which satisfy the conditions of the EVT. Functions that are continuous on a closed interval. And let's talk about some of them. Well, what is going to happen in this case? Well, first, before we get into some hard, complicated examples, let's draw a picture. So let's say we have a function. It's continuous on this closed interval here, and let's say the function looks something like this. So here, I think we can all agree this is a picture of a function that's continuous on a closed interval a up to b. So how does this function work? Well, note this function has a local maximum here and a local minimum here, but that's not where the the absolute minimum and maximum occur. So at A, we get this value here, which is the smallest, so the local minimum is going to occur at A, and it's going to be this value here, and the absolute maximum is going to be at this point here. So what does this leave us? What can we do? We just talked about finding local extrema, and now we're saying that maybe those aren't good enough. Well, luckily, this is all that can go wrong. So fact, if f at x is continuous on closed AB, its absolute extrema can only occur at critical points or endpoints. So what does that get us? The game is therefore very similar to finding local extrema. What you have to do is you have to look at your function, and for everything in the open interval AB, you have to find all of your critical points there. So you set f prime at x equal to 0, you find all of those points, or you find the points where the function isn't differentiable. Those are all candidates for your absolute extrema, but you have two additional candidates, the two endpoints, where absolute extrema may or may not occur. And that's how it goes. That's the process. Now let's go through a couple of examples. All right, so let's talk about, as an example, f at x, and we'll just do a function we talked about before, x cubed minus 9x, but this time on the interval -2 up to 4. All right, so how does this function work? Well, we know already what its critical points are. Its critical points are √3 and -√3, and these give values of, well, if you plug this in, you get that this is going to give you -6√3, and this is going to give you 6√3. So those are the two values there. So obviously this is a contender for the maximum, though it might not be, and this is a contender for the minimum, but it might not be, simply by virtue of the fact that the function value here is bigger than this one. But now we also have to plug in the endpoints, and we see that f of 2, -2 rather, when we plug it in, is going to give us 10, whereas if we plug in f of 4, we are going to get 28. So, as it turns out, our absolute minimum is going to occur at √3, and our absolute maximum is going to occur at 4. So let's just remember, what does this function roughly look like? It looks something like this, and we're cutting it off at around -2 and around 4, and just what we're saying is, well, we have this value here, which is a little bigger than this value here at -2. We have our absolute minimum here, which happens to also be a local minimum, but let's just continue the graph up a little bit. We have another value at an endpoint here that's bigger than this local maximum, and we have the absolute extreme maximum happening here. So indeed, here's an example where one of the local extrema is a global extrema, and one of the global extrema is not a local extrema. So that can happen. So you certainly have to check everything. You certainly have to be on your toes here. All right. So a second example, also with a function we've worked with before, is the following. So we can also work with, let's call it g of x, just because there's already an f on the board, is again this example, x squared plus x minus 2. And let's talk about this maybe on the interval -1 to 3. Why not? All right, so we have our critical points again from last time, and they are at 1, -2, and -1/2. And we can compute, well, we know that these guys had function value of 0. And so they are going to be our global minima, because of course this function spits out either positive numbers or 0 because of these absolute value bars. So right off the bat, we know that 2 points, 1 and -2, are both absolute minimums for this function. There can be more than one. We know also that this value, if we just plug it in, we're going to get 9/4. So now, what else is happening? What else is going on? Well, we just have to now check the endpoints and compare the values at the endpoints to everything else. So if we take g of -1, well, what do we get? We're going to get 1 -1 -2, which is going to be absolute 2. Absolute -2, rather, which is going to be 2. And we see that 2 is smaller than 9/4. So this left endpoint isn't a maximum or a minimum. It doesn't have to be, but indeed it isn't. Whereas if we take g of 3, what do we get? Well, that's going to be 9 plus 3 minus 2, which I guess is going to be 10. And we can see that 10 is going to be bigger than 9/4. So yes, this function does have its maximum at the right endpoint 3. It has a local maximum that's not a global maximum at -1/2, and its absolute minima occur at two critical points, 1 and -2. And that's how this one works.